In this project, I implemented a convolutional neural network to classify three different texture categories: wood, grass, and brick. All the images used in this dataset are tiny 32 cross 32 patches, which means the model must rely entirely on fine grained texture patterns instead of shapes. The purpose of this presentation is to walk through the dataset creation, pre-processing steps, the CNN architecture, the training process, and finally the evaluation using feature maps and the confusion matrix. The main goal of this project is to correctly classify 32 cross 32 texture patches into one of the three categories: wood, grass, or brick. For the method, I used a convolutional neural network because CNNs are extremely effective at learning, repeating local patterns and edges, which is exactly what defines a texture. The evaluation focuses on accuracy curves, the loss curve, the confusion matrix, and feature map visualizations. These tell us both how well the model performs and what kind of patterns the CNN actually learns internally. Since the images are so small, this becomes a good test of whether CNNs can capture fine scale texture structure.
The dataset is organized into three folders, one for wood, one for grass, and one for brick, as shown on the left. The pre-processing strategy involves manually resizing every image to 32 into 32 pixels. This ensures uniform input size, and it also forces the model to focus purely on texture patterns and not the overall shape of the object. The next step is rescaling pixel values to the range 0 to 1. This is important because neural networks train more efficiently than when inputs are normalized. Finally, the dataset is split into 80% training and 20% validation. On the right is the Keras data loading code. The image data generator handles both rescaling and splitting using validation split equal to 0.2. The flow from directory function reads image directly from the folder structure. The key point is that both training and validation generates use the same folder, but differentiate using subset equal to training and subset equal to validation. This is a simple and reliable way to manage small image datasets. The CNN architecture consists of two convolution and pooling blocks followed by dense layers. The first Con2D layer uses 32 filters of size 3 into 3. This layer captures basic patterns such as small edges and color transitions. Max pooling reduces its spatial size, which helps remove noise and prevent overfitting. The second Con2D layer uses 64 filters. Increasing the number of filters allows the network to learn more complex and detailed texture structures. This is especially useful for distinguishing between textures like wood grain and brick patterns. After flattening the feature maps, a dense layer with 64 neurons learns higher level representation. The final dense layer uses softmax activation to output probabilities for the three classes. The model is compiled using Adam optimizer and categorical cross entropy laws, which is the standard setup for multiclass image classification. On the right is the training code. The model is trained for 10 apertures using the training and validation generators defined earlier.
These plots show the training and validation loss curves. We want the validation loss to decrease steadily and follow the training loss without diverging too much. In this project, the validation curve stays fairly close to the training curve, which is a good indication that the model isn't overfitting severely. You can also see the loss decreasing over epochs, confirming that the network is learning meaningful texture patterns. Below that is the confusion matrix code. The model first predicts the class probabilities for the validation dataset, and then we convert those probabilities into class indices using argmax. The confusion matrix compares these predictions with the true labels. This matrix gives the detailed breakdown of which textures the model recognizes well and where it struggles. Typically, wood and brick are the recognized very accurately, while grass can sometimes be confused with wood depending on the lighting and pixel level similarity. Overall, the results confirm that the CNN has successfully learned to classify the textures.
The code on the left pulls out the outputs of all the convolution layers. The idea is to create an activation model that accepts the same input image but returns the internal feature maps instead of the final classification. Once we pass a validation image through this activation model, it produces a set of feature maps, each corresponding to how a specific filter responds to different parts of the image. On the right, we visualize these maps. Each small image corresponds to one of the filter's output. Some feature maps highlights strong edges and others react to the repeating patterns, color gradients or texture density. This CNN visualize confirms that the CNN is learning exactly the kind of information needed for the texture classification. It is focusing on local patterns rather than global structures, which is ideal for 32 cross 32 patches. The feature maps clearly shows that the model focuses on low-level characteristics such as edges, grains, patterns, and repeating shapes. The confusion matrix accuracy curves confirm good overall performance. Possible future improvements include using data augmentation for better generalization, increasing the dataset size, or experimenting with deeper CNN architectures. That brings this presentation to an end.